Today we're going to talk about objects that are spinning, but they're changing the way they're spinning, and the rate at which they're changing, how fast they're spinning, is a constant. In other words, constant angular acceleration. And we're going to develop a set of equations for solving problems with constant angular acceleration, and then we'll work some problems to solve it. So, but first, let's review the kinematic equations. For translational motion. Now, I'm going to use this as an excuse to review stuff that we did, 6 months ago, and we should start reviewing to get ready for the AP test, so that's cool. Well, here's what we said. Let's suppose we have our definition for acceleration. Acceleration is the rate at which we're changing our velocity. Okay? And what we did is we took this equation and we said, what is delta V? It's V final minus V initial, and so on. Well, we kind of can solve for this, and we can say that V equals V naught plus A times T. Okay, so this was our first kinematic equation. And then we made a graphical argument. We said if this is velocity as a function of time, let me zoom in. If this is, V equals V naught plus AT, well, here's V naught. The slope of this line is the acceleration at a certain times t. Here's our final velocity. So this is V naught, and this would be V final. And then we made an argument that the area underneath the velocity versus time graph is the displacement. So the area is our delta x. Well, this is a trapezoid, and the trapezoid basically said delta x, which is the area underneath here, displacement, is equal to the average base times the height. Well, in this case, the base is the initial velocity plus the final velocity divided by 2 is our average base. And then we multiplied that times time. And this was our second kinematic equation. And the only reason that this works is because this is a straight line right here, which makes this whole thing a trapezoid. Then what we did is this. We took this equation, we plugged it in here to substitute for the final velocity, and we got and then we cleaned it up, and this final equation was was our displacement is equal to V naught times t plus 1/2 a t squared. Then I took this first equation and I solved it for time, and then I plugged it, and then I substituted that in for time, and this got me an equation that didn't have time in it. And we wrote it as V squared equals V naught squared plus 2 times the acceleration times the displacement. Oops, a bit off screen. So, we derived, we observed this. Then we said, hey, the area underneath the velocity versus time graph is displacement, and then we use that area to derive this. Then we did a simple substitution of this into here to get this, and then we did another substitution for time from this equation into this equation, and we got that. So we just played little algebra games and derived the 4 kinematic equations that we've been using for constant linear acceleration. But here's the deal, and I don't need to go through the whole thing over again. I can do the same thing. What if our angular acceleration, let's do this for for rotational motion. Oops, let me zoom. Well, I'll just use this. Well, here's the thing. The angular acceleration is equal to the change in angular velocity over the change in time. You see, it's the same as this, only just different symbols and different units, and they mean slightly different things, but mathematically they have exactly the same structure. Well, this is equal to delta omega is equal to the final angular velocity minus the initial angular velocity, and we'll just call delta t our time t. And if I solve this for the for angular velocity, I get the angular velocity is equal to the initial angular velocity plus the angular acceleration times time. So this is the same equation as this. Look at that. Now, we haven't really covered it yet, but if I have a graph of angular velocity as a function of time, well, then I would graph it, and it would look like this. It's a straight line. This is a straight line. Y equals mx plus b. The slope of this line is the angular acceleration, and the area underneath this graph is our change in angular position. So basically, I'm just doing exactly what I did before, and I get delta theta is equal to the initial angular velocity plus the final angular velocity divided by 2, that's my average base of my trapezoid, times the height of the trapezoid, t. And that gives us the second kinematic equation. Delta theta equals omega naught times t plus 1/2 the angular acceleration times time squared. The final angular velocity squared is equal to the initial angular velocity squared plus twice the angular acceleration times the change in angle. So these are my 4 kinematic equations that I can derive exactly the same way I derived the translational kinematic equations for constant acceleration. So here, A equals a constant. Well, let me zoom out instead of going back and forth. And here, the angular acceleration is a constant. But it's the same argument. So look, basically, here's what you can do. And you can do this with a lot of rotational stuff that we're going to get to in a little bit. You have analogous variables. Wherever I see a final velocity, I put a final angular velocity. Wherever I see an initial velocity, you put an initial angular velocity. Time is the same. Time doesn't care whether you're spinning or translating. So now you can use these equations to solve problems that involve constant angular acceleration. Now, I would do this, just make sure that you keep the units consistent through the whole thing. The nice thing about the kinematic equations is that you can use degrees, you can use revolutions, or you can use radians. But you have to make a choice.
Can you use pi sectors?
Huh?
Can you use pi sectors?
Mr. Kinney, Mr. Kinney, say that is all.
That is all.